So in this example, we're going to use the log-log method to determine the exponents on the rate law. And we want you to find a couple of things. We want you to find the rate law, which involves getting those exponents. And then once we have the exponents, we're going to use one of the trial's pieces of data to substitute into the rate law to get the value of k. And then we've completed the rate law. We have the constant and we have the exponents. A tail end question that you could encounter on a question like this is a part C that would ask you to determine the rate of the reaction if the initial concentrations were. And that's simply giving you two more concentrations and say, all right, now use your equation to determine what that rate is. So that's typically the way a full rate law problem will end out. All right? Okay. So to begin with, we're going to set up our rate law with the exponents in it. I'll do that on the next slide. And then we need to look back at the data and pick our appropriate trials. Like I just stated when doing the log-log method, if I want to see how changing the effect of ClO2 affects the rate, then I need my OH concentration to be held constant. So if I'm looking for the effect of ClO2, I'm going to look for two trials where the OH concentration is constant, and we can see here it's going to be trial 1 and trial 3. So I'm going to analyze trials 1 and 3 to see the effect of ClO2 on the final rate of for the rate law. All right? And then in the second part of it, to determine the second exponent, I need two trials where Cl2 is held constant, and you can see there that it's trials 1 and trial 2, and there we've got the change in OH. All right? So I'm going to go ahead and we're going to start with this. So first thing we need to do is we need to write down a general rate law, and in this case, it's going to be R equals K, concentration of, what was it? It was a ClO2, yeah, ClO2 to the exponent x, and then OH minus to the exponent y. Okay? So I'm going to start with looking at ClO2 to the exponent x. In other words, I want to find x. And if I'm looking for x, I need two trials where the OH concentration is constant, and I need a reminder. I'll take a look at the data. Where's the OH concentration constant? Right, so that's trials 1 and 3, right? So I'm going to make a little note that I'm going to use trials 1 and 3. And so now we're ready to use the log-log method. We've already derived it. The log of rate 2 over rate 1 divided by the log of the concentration. And we could call it A2 over A1. All we need to do is make sure we're picking the right chemicals. In this case, the A is the ClO2. So now going to your data, and I've got the data here in front of me. I'm looking at trials 1 and 3. And it really doesn't matter, again, 2 and 1 are reference points. So I like to use 2 as the bottom one. So I'm looking at trial 3 for my position 2. So rate 2 then is the rate for trial 3. So that's the log of 1.16 times 10 to the minus 2. And I now need the rate for my initial trial, 1.3 times 10 to the minus 3. So there's my rates. And now I need the log of the concentrations. Again, I need 3 on the top. That's log of 0.0450 over, and then 0.0150. All right? So at this point, if we could just do the divisions, the log of what over the log of what? What do we have for numbers there? Has anybody calculated those divisions? The top is 8.9. Yeah, that's 8.92? 8.9, very close to 9. And what's the bottom? 3. So now we can finish the division. I'm putting my x back up here. I should have wrote that down. The log of 8.9 divided by the log of 3, and what do you get? Yep. Which essentially is 2. For our purposes, that's a 2. Which means our x is a squared. It's a squared relationship. And we can see that kind of by looking at our differences right here. Here's our differences. What this essentially says is that if I triple the concentration, this essentially says right here, if I have 3 times the concentration, then I'm going to result in 9 times the rate. And to go from 3 to 9 is a squared relationship. And what the log does is simply pull that number out and give it to you as a number on your calculator. It means you don't have to think about it so much. All right? Let's look at the second half of this. So here we're looking at OH minus Y. We're looking at trials, what did we say, 1 and 2? I think our CO is constant there. Yep. Trials 1 and 2. Now, you know what? You don't have to write the equation out each time. The rates go on the top and the concentrations go on the bottom. I like to put the 2 on the top and the 1 on the bottom. So I can go straight to log, and this is going to be for Y, and I'm looking at the rates, and I'm putting the 2 on the top. 2.60 times 10 to the negative 3, and 1 on the bottom, 1.3 times 10 to the negative 3 over the log, and now the concentration changes. Again, 2 on the top, 0.050, extra 0 on there, and on the bottom, 0.0250. Log of what over what? So I'll take the numbers as they come in. I'll take that top number first, would be nice, but it doesn't matter. Mike, what do you got?
Log is 0.5.
So this is 0.5. I think you've got that upside down. This is looking like it's almost twice as big as this, right? 2.6 and 1.3.
I have it upside down.
Yes, it will be 2. 2. What do we have on the bottom? 2 and 2. The log of 2 divided by the log of 2, well, that's not too tough. That's 1. And again, if we analyze this, think about what this means. This means times 2 for the concentrations. If I double the concentration, I get times 2 for the rate, and that is a linear relationship. We expect an exponent of 1. Okay? So we've got our exponents. Now all we need to do is rewrite the rate law and solve for the constant. And I hope I have one more blank slide. Yes. So now I know that rate is equal to some constant K, concentration of ClO2 to the exponent 2, concentration of OH negative to the exponent 1. Doesn't need to be written out, but I put it there just to kind of stress it. Now I'm going to rearrange and solve for K. R over, I'm going to bring these 2 over and underneath. ClO2 concentration squared times the OH concentration to the exponent 1. And that's equal to K. And now it doesn't matter which trial I take. In a real experiment, it would. Each trial would have a slight different variation due to errors within it. But because we're giving you simple, perfect data for introduction of this concept, you just need to take any of the trials, and because I'm quite lazy, I only look at number 1. So looking at number 1, 1.3 times 10 to the minus 3 over the concentration of ClO2, 0.0150. That's all squared. And then the concentration of OH, 0.0250. And that's to the exponent 1. And that gets us K. And again, once you have that value, I'll take it. I should record the clacking of the keys. That'd be cool. Again, don't worry about the units for the constant. They will have units, and each constant has its own set of units because it's dependent on the exponents. When you get to university, your university professor will have you worry about the units. We're not worried about it here. Somebody have a number? We got to start somewhere. Amelia, what do you got? 231? Thumbs up before I write it down? Yep. So 231, we actually could probably round that to 2 significant digits by the looks of it. 231. Now we'll leave it at that. That's pretty good. And now we can complete this whole process by writing the rate law out completely. Rate is equal to 231 concentration of ClO2 squared, and I apologize running out of room, I've got to go underneath, times the concentration of OH to the minus 1. All right? Sorry, not to the minus 1. Concentration of OH negative to the exponent 1. Yep. No, you don't. You don't have to put that 1. Yep. All right? So that's how we do a rate law problem. Like I said, the only way that this question could be a little more complicated is if we now asked you, what would the rate be given these 2 concentrations? You substitute them in, use your K, and you get an answer for the rate. All right?